Okay, guys, let's look at these. First one would be this alkyl chloride here. Stereochemistry would be racemic because of the SN1. How do we do? Questions?
Is that the same as steering like one of the stereochems and then putting both?
Yes.
Okay.
Racemic means you get both 50-50. Chlorine would be going back and forward, both a DL pair. Carbon is chiral. Questions how we got to that?
Just to walk back through the process, so HCl is,
Mechanistically, we protonate the OH.
yeah, And the
Since it's
OH
SN1,
leaves.
water leaves cation,
yeah.
and then the Cl minus attacks the cation from either side. That's why you get either enantiomer or both enantiomers. How do we know it contains chlorine? I told you the mass spec had a significant M+2 peak. Why did I have to tell you that? I kind of had to tell you that because there's another product you could have showed here. You could have showed something without a chlorine. Could have showed that as a product. What mechanism would this have been?
Elimination.
E1. That is, once we make cation, instead of chlorine adding to the cation, something could have taken this, maybe even a chloride. These electrons take here, these move in here, we get the alkene. That's reasonable. So I gave you some information though that tells you that compound contains chlorine. Yeah? Okay. Mechanism. Now that we know it's substitution because the chlorine replaced the OH and not just eliminated, well, was it SN1 or SN2? Could you tell if I didn't give you any information? Could this have been SN2? We protonate, okay? What if the chloride had just come in here and did this? SN2, and we would have gotten inversion. We would, not racemic, but it would have been only one. Is this possible? Question is this a strong nucleophile?
No.
Well, we said strong nucleophiles with anions, or sp3, sp2 nitrogen. Is that an anion?
It is, but you specifically said that the
But what if I didn't say this? Could it have been SN2? Yeah. By the way, that's really not a strong anion. That's sort of an exception. But we already said anions. So you're like, well, but that's strong. Well, I gave you some information. And the information says what? If we add more Cl minus, the rate doesn't change. If we add more nucleophile, the rate doesn't change. So what does that tell you about the nucleophile? Not the rate of turning step. So your mechanism is SN1. And SN1 leads to racemic. Yeah? How we do on that?
I did an SN2.
You're
Question?
saying it's not stereo-specific.
Saying it's not what?
Not stereo-specific, is that the same thing as saying?
Not stereo selective, I think. I'm not. There is a difference between selective and specific. I'll probably be able to tell you the definitive difference once I've thought about it. This reaction is not stereo selective. You get both enantiomers. SN2 would have been stereo selective. One equivalent base is going to deprotonate the more acidic proton, carboxylic acid. That becomes an anion. The anion kicks off the chlorine. We make this bond here. There used to be a chlorine bonded there. Now there's an oxygen bonded there. Good old SN2 after first making the nucleophile stronger. How we do? Who reacted this deprotonated down here instead? Why? Phenols are not as acidic as carboxylic acids.
I thought that the resonance made it worse.
We went over that. Yeah, there's more resonance here, but the resonance puts the oxygen on the anion on carbon. Okay? Thomas, where does the resonance put the charge here? You said this a few days ago. Puts it on other oxygen, right? Yes. We went over there. And I told you that often you guys think phenols are more acidic, but this is why they're not, et cetera, et cetera. You guys gotta watch the tape. Okay, question?
Can you restate why you chose chlorine instead of bromine?
Because that's a tetrahedral carbon. Bromine's not on a tetrahedral carbon. Yeah? You didn't displace that one, did you? Why?
Well, I was going off of,
Bromine's better leaving group?
yeah.
Yeah, but it's got to be on tetrahedral carbon. You ain't going to leave sp2. No, you're not going to do any of the mechanisms we're doing on this. This is not a leaving group for any of the mechanisms we're doing right now. Tetrahedral carbon. Here. SN2, right? Anybody do SN1? You would have got the same product if you did SN1, but it's not SN1. You know, although that would be a resonance stabilized cation, but you got a good nucleophile. Good nucleophile bullying. It's going to be involved. Here I come. Question?
Okay, why did you do a Fisher reaction?
For that reaction?
Why do we need a Fisher projection for this reaction?
Oh, is that for the other reaction?
Do I? This is for the one below.
Oh, okay,
I went up that.
That's Newman. Circle, circle, dot, dot is Newman.
Oh, okay.
Fisher is the crosshair. Let's see, I got a strong base / nucleophile. I got a leaving group on what type of carbon? Okay, yeah, it is tetrahedral, but what type of?
It's a very sterically hindered.
Tertiary, okay? So is this SN2? First off, since it's strong, it's bimolecular. SN2 or E2?
E2.
Can you do SN2 here? No, so ding, ding, ding. Like an E2 reaction, E2 elimination, right? To make an alkene, okay? Is the base sterically hindered?
No.
No. We're going to have any trouble taking the more hindered H to make the Sate-Sep product? No, you won't have any trouble with a non-hindered base. We're going to get the Sate-Sep. That's the one you want, unless there's a reason you can't. Now we've got, so where is the H we need to abstract to get the more substitute alkene? I drew it in here. That's one beta hydrogen. The other beta hydrogen is here. But removing that would put the double bond here, and it would just be disubstituted. Removing this one would give trisubstituted. So we want to eliminate HBr and put the double bond in there. If you put the double bond in there between these two carbons, but you got stereochemistry. That is, are the methyls cis or trans? Well, in the product they're trans, but they could have been theoretically cis. How do we determine this? I did a Newman. I drew what I saw. Ethyl straight up, H to my left. Ethyl straight up, H to my left. Back carbon, methyl straight down, bromine to my left. Methyl straight down, bromine to my left. There it is. Right now the H that's eliminating the Br are not anticoplanar. They're neither of that. I rotated the back carbon. Got up here. Now the H and the Br are anticoplanar. That's when the elimination takes place. Everything is stuck when that happens because it's all concerted. The phenyl and the methyl are on the same side. The methyl and the ethyl are on the other side. Phenyl and methyl, same side. Phenyl and methyl, same side. Ethyl and methyl on the other side. So there you go. Actually, the methyls are trans. How'd we do?
Do you have to necessarily draw the Newman projections?
Directions did not say you had to draw Newman.
No, I mean like,
Directions said you had to show the major product.
yeah, okay.
Did you get the?
Yeah, I got the point. I just went to the stereochemistry of it. I said that both of the phenyl and the methyl are on the same side, so that's when I eliminated that.
The phenyl and the methyl on the same side?
Because of the stereochemistry, they both were going back. Yeah, I'm not sure if that's like the right thinking thought process.
Yeah, but the
Yeah, I eliminated with that.
H and the Br are, how do you know when they're anticoplanar?
Yeah, then we would need a new, but I kind of did. And that's just
I don't know, you may have just,
not lucky.
well, you got a 50% chance of getting it right if you know what alkenes are forming. Whatever works for you. I'll show you the way I recommend it. And I don't recommend any other way, but I recommend this way. But if you have a way that works for you, that's great. Maybe someone showed you a different way. Whatever works for you. This is the way I recommend. Question? Okay.
Good question. I thought the E2 was supposed to be on the least substituted alkene, or am I confused about it?
No, I mean, that would be called the Hoffman product. 6F is preferred. Sometimes you give Hoffman with E2 because maybe the base is very bulky. But also the anti-coplanar requirement. Sometimes, because you have to meet that requirement, sometimes you get now this is actually the best of the two alkenes, because if we put the phenyl and the methyl and the ethyl on the same side, that would have been less favored, because big groups are on the same side. So we actually got the better of the two alkene stereoisomers. But it wasn't because it's better, it's because it met the reaction requirement, the anticoplanar requirement. Okay, how do we do on that one? Fastness in a sulfolysis reaction with ethanol. How do we do?
I didn't get it right. I didn't get that one.
How do we do? Question?
I thought it would go best on the 1' bromine because it's a good leaving group.
Which one?
That one.
This one?
Yeah.
Yeah, what did I get that one?
ETOH is a weak base and a weak methyl.
We're reacting with ethanol. That's weak. Weak is going to be, it's too lazy. It sits on the sofa. It's not strong enough to be involved in the rate determining step. You need a strong base / nucleophile to be involved in the rate determining step. At the same time, if it's strong, it's also going to be involved because it's a bully. This is a unimolecular reaction. That is, it's carbocation chemistry. The first step is just leaving group leaving to make a cation. The question is really which one of these is going to ionize the fastest to give cation.
Most stable pattern.
This one. Not only would it be tertiary, but it would be resonance stabilized. This one would be resonance stabilized, but it wouldn't be tertiary. That one's no go. That one's not tetrahedral. Why is this one better than this one? Bromine's inherently a better leaving group. That means it's inherently more willing to leave compared to the chlorine. There's no resonance here. It'd be tertiary, but there'd be no resonance. You can't draw resonance structures here. How do we do? Mechanism. We got we're losing oxygen. We got two OHs. You can protonate and ionize to make tertiary cation, or you can protonate and ionize to make primary. Yikes. I'd probably make tertiary. Protonate, yeah, ionize, make tertiary cation. We are doing that, right? Because we have no nucleophile. I mean, it's carbocation chemistry. Leaving group leaves. We're going to make a ring. This attacks, but if this attacks there, that'd be a 7-member ring. We need a 6. Hydride shift to give cation there. Now we can come around here in this weak nucleophile. Now I know at least one of you did this. Who turned this into an oxygen anion, minus? Thanks for letting me know. Why did you turn that into an O minus? To turn that into an O minus, you need a strong base. Actually, hydroxide won't even do it. If hydroxide won't do it, how will sulfuric acid do it? No, but that's a common thing. It doesn't need to be an anion to be a nucleophile. It can be a weak nucleophile. Attack here, what does that give? Where are we at? You're going this way, made the bond, still got the H. Now you can remove the H. But you're removing the H from a positive oxygen, not from a neutral oxygen. And we can do this, we've done this a lot, to reform our, actually this is catalyst. That's catalyst. If we balance this, what do we form other than our product? Water, yes, we form water right here. Right there, we form the water.
Why can't we reform H2 as a
I did. Right here I did.
Thanks. Do you have to reform the water though also?
You have to reform the what?
The water.
Reform it? We didn't reform it, we just formed it. Boom, water was formed. We got this and we formed water. I just drew it up there in terms of what clarified. We showed a balanced line reaction with everything there. Yeah.
So I had the OH leaving group leave, but then used the OH minus to take the hydrogen away.
OH minus? No, that's a poor leaving group. It's not just going to leave. OH is a poor leaving group unless you protonate it or convert it to a tosylate, but that's a totally unique reaction where you're making something brand new. When we make this in a mechanism, you're not isolating. You're not isolating any of these. When you do this, you start with this and then you isolate this. This is actually a poor equilibrium. The equilibrium favors that. But guess what? When this gets pulled on, this equilibrium adjusts and makes more of this. So it gets pulled on because it continues on. Okay. There might have been a mechanism just like this on test 2 with alkenes. We could have gotten to the same carbocation and then did the same thing remainder way back then. And in fact, you probably saw mechanisms like that. Boom, 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 boom. What if I had this alkene here? I could have started with this, that alkene and did the same chemistry. We're doing carbocation chemistry by something leaving. How do we get carbocations back over here? H plus. Are we going to make cation on the left or right? We should now be able to clearly answer that. They both look like they would be tertiary, but one's better than the other. When this attacks H plus, we're going to leave cation on the left or right?
Left.
Correct. Why?
It's resonance.
It'd be resonance stabilized. So this attacks H, leaving cation here, new H there. Well, guess what? What's that there? New H here, cation here. That is, you can get carbocations from alkene chemistry. You can also get carbocations from leaving groups leaving. And once you get your carbocation, then it's, you do the same thing from there. Because once you get carbocation, it's prone to rearranging, hydride shift, ring expansion, etc. You see that? How the alkene carbocation chemistry and leaving group carbocation chemistry? SN2 below, so it's the rate equation equals concentration of both reactants. Yeah?
And is that because of the heat or because of the,
Strong nucleophile.
yeah.
Cyanide. Bully. Here I come. I'm not waiting for you to ionize. By the way, it ain't going to ionize anyway. Why not? Because it's what?
It's not.
I can't hear you. Still can't hear you.
It's a good thing, she said it's not a good leader.
Bromine's pretty darn good leaving group.
It's not.
In general.
So it's good, but it's gonna be a
Primary cation. You said that? I can't hear.
He said it.
I imagine other students can't hear. It makes primary carbocation. So it ain't going to go, it's not going to just ionize and do SN1E1. You're going to have to kick that off with the strong nucleophile. That's an SN2. Yeah? Second one, 43. How we doing? Questions? Questions? Question?
Since both of them are 43, would it matter which one is the cation and the radical? I think they both weigh. I think they both weigh 43.
What are both 43?
The cation and then the radical.
Okay. What about it?
So how do you know which one is the cation?
The cation would be you want to make a resonance stabilized cation. It's called an Elim ion.
What about the second from the end? Would that be resonance stabilized as well?
Second from the end.
Yeah. Wouldn't that be 43 as well?
Oh, if you cut it,
Yeah, I got it.
Yeah.
it won't add up to be 8.
No, it wouldn't be 43. How would that be 43?
Will you put, like, on the line?
I think it'd be 45.
Yeah, it's just, okay.
I think, added up. The two on the end, by the way, are 88. The molecular ion was 86. Did you see that?
No.
Did you recognize that these have different molecular weights?
I just ran out of time.
Well, that's very important. Look at them. The first three have 1 degree of unsaturation. The second two, no degrees of unsaturation. They all have the same number of carbons. So that should tell you very quickly that the last two are going to have 2 more H's. Because they don't have the degree of unsaturation. I added it up at the end, it's 88. The two on the end are 88, the other three are thus 86. They're missing 2 H's, 1 degree of unsaturation. Molecular ion was 86, so I quickly got rid of those two. And if it cleaved, I think it'd be 45, not 43.
Yes, sir.
My line is not a cleavage, although it actually lines up for cleavage. My line is more of an X. I was Xing them out.
Okay, other questions about that one?
Yeah, can you go back real quick to the last one you doing?
Mass spec?
Yes, sir. So the same one, second to the end, if you please there to, tertiary carbocation on the carbon?
This one here?
Yes.
There'll be no tertiary chromocatione. Be secondary.
Okay.
Over here?
That's just a block.
Right, okay. That wouldn't be tertiary? No? Oh, okay.
That's not a bond, that's my line.
Okay.
If it was, it'd be C 12, 20, 24, 36, and 7. It'd be 43, yeah. It'd be 43. Problem is, where's your 88 for the microion?
Okay.
Microion shows 86. Also, you're claiming that that cation would be more favorable than cation here, which would be resonance stabilized. Typically, you want to predict something and then be rewarded by your prediction. Wouldn't be so good if what I'm trying to get you to predict, then it wasn't what was needed to predict to get the answer. But the main thing again is this compound looks like it has a molecular weight of 86.
One thing I don't get is in the, when it's breaking
All right, I
apart.
can hear now.
When it's breaking apart, it loses 15 and then it loses 28. And it makes more sense that it would lose 29
What do you mean?
in the two short peaks. Like when it.
Oh, you're looking at other peaks.
Yeah.
I didn't even do that. Okay. It lost what? 86 to, it lost 15?
Lost 15 and it lost 28. And
M minus 15.
it's lost one.
Okay. Would the one we circled, could you envision losing 15? Yeah, another alpha cleavage on the other side. So that makes sense, but then you're saying it lost how much?
It lost 28.
Okay, well 28 is an even number. That's not just a plain cleavage of a radical cation. That's more like a Merclafferty or something.
Okay.
That can do a Merclafferty. If it did a Merclafferty, I think it would lose 20. It would lose 28. That's a Merclafferty.
Okay.
So there was also an M minus 15 here, which is also predicted for that answer. Okay, guys. Test tomorrow. Hopefully that helped a little bit.
Yes.
See where you're at. Let's finish up the elimination handout, a few miscellaneous things. Which one of those at the bottom is going to be faster? Anybody? Which reaction would be faster? B? Why? Why does that make it faster?
More favorite products. It goes in reverse.
More favorite product if it was going through.
I mean, like you want to be more in trans than cis.
Why would that make this faster?
Do you have to draw a chair to these reasons?
Okay, let's go back 2 or 3 weeks ago. I don't know how long ago it was. What do we know? This is an E2, right?
Yeah.
The H is being removed, and the leaving group have to be what? Okay, let's draw this. Chair conformation so we can see this. Okay, let's put the iodine here. For it to be anticoplanar with a neighboring H, the leaving group has to be what position? Axial. So let's draw the iodine there. Axial. And the H here, we'll call that HA. These are trans to each other, yeah? One's up, one's down. You see it here? Over here we can do it like this. There's the HA. The tert-butyl is 1, 2, 3. One is here. If I do the iodine like that, how do we want to draw the tert-butyl? Equatorial. These are trans. These are trans. Okay. This is how it has to eliminate from this conformation. Let's draw this one up here. The iodine has to be like this. The H has to be like this. Okay? If the iodine is like that, we're up here. How's the tert-butyl? Also axial. These are cis. These are trans. Okay. Now we know that these can exist in ring flip. Look at these two. Which one is more likely to ring flip? Yes, the top one. Why? And the iodine. Yeah. But, okay. Yeah, but, okay. This one will ring flip. When it ring flips, what happens to the iodine? It goes equatorial. Can it eliminate in that?
No.
No, it can't. The question is really, which one is more likely to exist with the iodine axiom? Top or bottom? Bottom. Because when it's axial, the T-butyl kind of is happy there. It's like, okay, I don't mind you being there. This compound is more often going to exist in the bad conformation, the conformation that it can't eliminate from. This compound is more ready to go. It's more existing in the conformation that's ready to go. It's going to be faster. Is there anything else that would enhance, that would affect the rate? They're both, the H is really not encumbered any differently. This is typically the answer. The answer is this one. B will be faster. But it's because this one is going to be more in the correct conformation. Make sense? What other product could be formed in reaction A? Well, that's hopefully pretty easy. What else could we have gotten there? Elimination product. We could have got double bond up there. Because there's beta hydrogens up there. Both of these are disubstituted, so I don't know which one's going to be favored. We could find an argument for one being favored over the other, but they're both disubstituted. Okay. From here on out, there's a variety of miscellaneous things that sort of bring in both elimination and substitution. Okay, first thing, heat favors elimination due to entropy. That is when you're looking, is it going to be substitution or elimination? Heat favors elimination. You take this compound with water and heat it, just like heated it in water. Most likely product with a lot of heat is going to be the elimination product. By what mechanism is this? E1. So which alkene do we get? The best alkene you can draw. And that's it. There's no stereochemistry there, but it's the Subst product, right? Plus HBr plus water. Now, if you want the water to take the proton, fine. Make H3O plus and Br minus. But that's how HBr exists in water anyway. Okay. There's more entropy with elimination. Now, up here, we can just get rid of the water because it doesn't really change. One molecule going to two. Okay? So, entropy is increasing. So, is entropy positive or negative? Are you positive? I think it's positive, right? And positive entropy is a good thing. Okay, yes. Okay. Now in your Gibbs free energy equation, which term does temperature magnify? Entropy, T delta S. So if your entropy is good, how do you make it even better? You heat. So you make a good thing even better. And then you're making that thing contribute even more to the outcome. Heat promote, if you're entropically favored, heat is going to make you even more favored in the Gibbs free energy equation. Okay? Because we could have also done an SN1 reaction here. Both mechanisms involve just ionizing cation. Well, couldn't a water just attack cation? You would end up with an alcohol, be SN1. What we're saying is, the more heat you give, the more likely you're going to get elimination. Because if you add water here, you're not going from one molecule to two. You're going from two molecules to two. Okay? If water was involved. All right. Well, the SN1 is shown below. So if you're having trouble with this going, it's not reacting, do you want to turn the heat up and think that it's going to make it react? No, you're going to make it go to elimination. Okay, here you go. Temperature magnifies entropy. Okay, number 2. Involvement of a good nucleophile will favor substitution. For nucleophile, you'll typically get elimination. Look at these two alcohols. Reacting with HBr, you're going to get the alkyl bromide. Substitution. Reacting with HF, you get elimination. Well, what's the nucleophile here? Br minus. Pretty good nucleophile. Down here it would have to be what if we got substitution? F minus. F minus is a pretty poor nucleophile. It holds on to the electrons. And actually, when we're doing alkene chemistry, we used HF sometimes because we said F minus will never do anything. Poor nucleophile. You're going to get more elimination. In both cases, what are we doing? Protonate, ionizing. Right? Here's where it differs. Good nucleophile will add as a nucleophile. and give you a substitution product. Bad nucleophile typically won't act as a nucleophile, but instead it'll act as a base. What do we got to do? Remove an H from here? And you'll do the quick, fast beta elimination of the E1. You get your alkene and you just reform HF. So HF is actually just a catalyst here. Here's the common cation. Now, for example, a common reaction of alcohols is to dehydrate them, to make alkenes. When we go from here to here, we have removed water. It's a dehydration to make an alkene. Common reaction of alcohols, commonly done with something like sulfuric acid. And this would be an E1. Protonate, ionize, and then something takes the H to put the double bond in, E1. You would not use an acid like HI. Protonate, ionize, cation. Iodide is a great nucleophile. It will attack the cation, and you'll get a substitution product. You'll certainly see this reaction. We're really doing this reaction right now. But in Organic 2, when I do Organic 2, we cover the chemistry of alcohols in particular, and we revisit this reaction. It's an E1 dehydration using an acid, but you don't want a good nucleophile. That would come with a good nucleophile. This would be an E1, of course. By the way, alcohols never undergo an E2, right? Somebody tell me why. Somebody tell me why you can't replace this by E2 in a single reaction. Why?
When you protonate, it's a bad lead.
Tell me again.
You have to protonate it first.
You have to protonate it. Well, can't you protonate it and do an E2?
Why not?
Or no?
Why can't you do that?
What does E2 require?
A strong nucleophile.
Well, but it's acting as a base, so we call it a base. Strong base. How do you protonate an alcohol?
Strong acid.
With a strong acid. Okay, so you've got to do a reaction where you need a strong acid and a strong base. You've got a big problem here. You can't have both in the same reaction. They're just going to react with each other. So if you think about it, you cannot do an E2 with an alcohol, because it requires an acid. Right? That's an E1. I mean, that's carbocation chemistry. A more sterically hindered base will favor elimination over substitution. We've kind of mentioned this before. For example, which base is best for this reaction then? Base is best.
The sodium butanol, T-butanol. Wait, what are we trying to answer?
Yes.
Yeah.
Why is that best?
Is this easier?
Well, if you used ammonia, could ammonia do this reaction? Ammonia's a good base.
But we want a sterically hindered base to get the E1
Why?
product.
Why not use ammonia?
As a Hoffman product.
There's no Hoffman. There's only one alkene you can make here. There's only one alkene.
So-
We're not trying to get Hoffman versus Satesef. We're just trying to get elimination versus what?
Substitution.
Substitution.
Oh, that's why.
See, if you're using ammonia, it could just come in here and do a substitution. So could hydroxide.
Yeah.
What does it say? A more hindered base favors elimination over substitution. Where you get some ambiguity is once you get two possible alkenes, if you have both a Satesef and a Hoffman, then then this could maybe start giving you the Hoffman. Then you could say, well, what if you wanted Satsef only? You'd use a less sterically hindered base.
But then you could do S.
Do it.
But then you could do S2 as well.
But then you might get some substitution. There's always going to be some competition.
So just write something down on the test.
No.
We'll get some
In some
points.
cases, like on the very first one on the quiz, I gave you some information to help you predict the stuff. And a lot of this is relative, not absolute. Once you see it, okay, these could give you substitution. In this example, you don't have to worry about Hoffman or Satsef.
You want elimination.
You just want elimination. There's only one possible product. And the H's you're removing are not sterically hindered. So I choose the base on the end. How did we get to G so fast? Did we skip something? Is it Miss Leonard? What was,
Yeah, we did.
where were we on? E, F. Oh, all that was under F. Okay, for some reason we decided to go to G. Clever ways to make ionization of an alkyl halide to a carbocation faster. Clever ways to make a halide a better leaving group. We know how to make an OH a better leaving group. You protonate it with strong acid. Have we ever talked about making a bromine a better leaving group? No. We just said it's a good leaving group. It'll leave. But maybe sometimes it's a little sluggish. Maybe it's going to leave and make a secondary cation, and the secondary cation is not that favorable. We know we can do it. Well, it's kind of a little clever, but we can use silver ion. Usually in the form of silver nitrate, which is usually soluble in water. If we didn't include that, we can react this with water, maybe do an elimination. That is, what's the first step of this?
Bromine leaves.
Leave, but it's going to make a secondary cation. Maybe it's a little slow. Silver ion will help. Silver ion really loves the halogens. Now you typically do not protonate a halogen like you protonate an OH. This looks like an H+. I'm not going to show this like we do H+, but there's some type of, there's some attraction here. Electrons are negative, that's an ion, yeah, but, okay. This attraction kind of makes that bromine like, ooh, I don't mind leaving, because okay. Got somewhere to go. Now this is not scientific mechanistic jargon, somewhere to go, but hopefully you get the idea. It will ionize off and become what? Silver bromide. Now these are no longer just ions, because what do we know about the solubility of silver bromide in water? It will precipitate. You learn in Gen Chem that your silver halides are insoluble in water. So the interaction, it sort of helps ionize and give you your cation, and this is faster than without the silver ion. There's your silver bromide. Then from here we can take the proton, water can take the proton, or nitrate, because we got nitrate around, right? I mean, if nitrate takes the proton, we can make nitric acid, and then water really didn't do anything. Of course, how does nitric acid exist in water? H3O+. So you can use water and just keep the nitrate ion. So the silver ion acting to facilitate the ionization, it accepts a lone pair called a Lewis acid. Something that accepts a lone pair, Lewis acid. Silver ion is a Lewis acid.
Maybe I'm not getting it, but I understand why it would be E1 or E2 because it's a leak, because it's silver nitrate.
E1 or E2?
I mean E1 or SN1.
Correct.
But how do you know that it's E1 without it,
And not E2?
without, or it not SN1?
SN1? It could be SN1.
Okay. You just gave the E1 product. Just,
Yes,
okay.
yes. Good question. I could have showed an SN1 product. Yes. E1 and SN1 always compete. There's way to make the elimination more favorable, such as what? Heat. But they're always competing. Yes, you recognize it. Good. I just showed an E1. I could have, yeah.
This might be a dumb question, but why doesn't it hydration at this point? Or like, would it give the same product?
Okay.
Or tertiary?
No, that's a good question, but let's look at it. If it did a hydride shift, right here, now if we're doing elimination, what are we going to form? H2O or nitrate, same product. So when I put it together, I didn't really rethink the mechanism, and then when I was just discussing it, yeah, but you're right, you recognize the hydride shift, but then you also said that it's going to get the same product. Now, for some reason, it could have eliminated over here now, and that would have had to come from the hydride shift. If that's different, then yeah. Yeah. Carbocations are always prone to what?
Rearrangement.
No matter if you make them from alkenes, or if you make them from leaving group leaving, or the next way you learn how to make carbocations. Any way you make carbocations are always prone to rearranging. This is just a clever way. It can also be used as a chemical test. Because the silver bromide precipitate, or silver halide, tells you must have had a halide there that was ionizable. But you're not going to get a precipitate with anything else other than silver halide. At least nothing that's common enough to ever be seen. Question, which compounds below would give a positive silver nitrate test? Positive meaning you got a precipitate. Which one of these would give a precipitate with silver nitrate? These three would. Because all three of those, the bromine can leave. Leave. Join up with the silver to make precipitate, secondary cation. Leave. Join up with silver to make precipitate. Tertiary cation, it's also resonance stabilized. Resonance stabilized there, they can all leave. Can this one leave?
No.
No, not a tetrahedral carbon. Ain't going to leave. So you can throw all the silver ion you want at it, the bromine ain't going to leave and form up and make the precipitate. This will not give a precipitate. Negative test. Those three will. Of those which would give precipitate, these three, which one will give it fastest?
The one in the middle.
Middle one. Your cation would have what properties?
Tertiary. And resonance stabilized.
Resonance would make it,
Oh.
the resonance structure would be secondary. Secondary. This one would be what? The initial would be primary, but resonance would make it secondary, which is better. Are you guys seeing that quick? You'd be able to see that. The initial would be primary. When you did your resonance windshield wiper, then it would be, yeah, primary and secondary. Which is better? Tertiary secondary is better. That bromine really doesn't need the help of silver to ionize. But if you give it some silver, it's going to be very fast to ionize. the little idea of silver. So the discussion starts in Gen Chem when you learn what a Lewis acid is, when you learn solubility rules. Then we see application here, using solubility rules to have a chemical test. We also have some organic mechanistic knowledge. Two, what are we under? One was a clever way to make, this was all under what? What is G?
Clever ways to make ionization.
Okay, so the first one was using silver. Okay, another clever way to make ionization faster is use a polar solvent. ACL, what happens when you put it in water?
Ionizes.
It ionizes. It makes H3O plus Cl minus. What if you put ACl in something like hexane? It won't. Right? Don't discuss such in Gen Chem when you talk about ionization of acids and stuff? Why water? Why does it ionize in water?
Polarity.
Water's polar. It's able to support the ions. The ACl wants to ionize because of polarity, but it's got to be in an environment that supports the ion. And so when it ionizes in the water, it coordinates with it by IMFs. And it hugs the ions, and everybody's happy. Try to make ions in hexane, hexane's going to be like, I don't want any ions. And so the system isn't facilitated. And that is, the transition states become too high and everything. Same thing with carbocations. Okay, you try to do this reaction up here, get this substitution product that looks like an SN1 because your nucleophile is weak. The first thing we need is for this to ionize, right? You can include some silver ion in here, or you can also use a polar solvent, such as acetonitrile and DMSO. These are polar, happen to be aprotic solvents, to support the ion, the carbocation, supported by a polar solvent. If you try to do this in hexane, probably is not going to react. Hexane is not going to support the formation of this ion. You see, there's a transition state leading to this. And that transition state has certain charges, and a polar solvent can sort of start coordinating with it and lower the energy of the transition state. Hexane ain't going to coordinate with anything. Make sense? Polar solvents facilitate ionization. Questions before we move on to deuterium. Deuterium's a little bit more than just a 2-minute blurb. It's a little bit more involved, and we'll do reactions using deuterium. Any questions up to this point? We'll meet this afternoon at 2:30 in this room. It should be available. Turn in your group report, yeah. Test tomorrow. What do we have? Nomenclature of dienes. Some multiple choice. Line reactions predict the product. Those could be give a reagent, or it could be give the starting material. Short answer, we have mechanisms, and there'll be mass spec. Topics, we had resonance, drawing resonance structures, understanding consequences and use of resonance. Dienes, we had 1,2 and 1,4 reactions, additions of conjugate dienes, kinetic versus thermodynamic product, Diels-Alder reactions, mass spec, then we had substitution and elimination. Questions?
I have a quick question on the Williamson ether.
Uh-huh.
So in the book it said it's a 2-step mechanism, but we only showed 1 step. So if we show it the way you showed us, then
No.
without the
What?
because in the book it actually showed how you protonated or deprotonated. We
You
didn't
gotta
really show
you
that
gotta
with the-
deprotonate your alcohol to make it into a nucleophile.
But when we showed it, like when we did it in class, we did do that step, so it really.
No, we did. We did it, we used either hydroxide or we used sodium metal. When we use sodium metal, you produce hydrogen gas.
Right here. Before we do the substitution, we first have to remove the proton. What base did we use to remove the proton? Was it either KOH or NaOH? We used KOH.
Oh, see, I was talking about.
Well, tell me what you're talking about.
When it says provide glue.
I mean, I could just show this, but this would have to come from deprotonating something.
But that's what I'm asking, do you want us to show it or not, or does it really matter?
I mean, if you're doing a synthesis, yeah, you need to show how you form.
Okay.
It probably said from an alcohol. It says from an alcohol, and alcohol is this. That's not an alcohol. This is an alkoxide. So start from an alcohol, which that's what a Williamson ether is. If you start from an alcohol, you first have to make the alkoxide using most commonly sodium metal. Other questions?
On the test, will we be expected to know, like, or will you put like SN2 under the arrow like that, or will we be like expected to know looking at what we're reacting with, what kind of reaction?
I don't quite understand. Will you be
Like,
expected
will
to
you-
put SN2 under the arrow?
No, like, will you put like this is an SN2 reaction, or will we be expected?
Well, just like on the quiz.
You'll give us-
Well, on the first one, I gave you some information because it looked like it could be either SN1 or, well, it could either have been really a variety of things. It could have been all four mechanisms. So I gave you some information. On the second one, I didn't give you any information. And the third one, I didn't give you any either. For example, the third one on the quiz, you had to arrive at the fact that it was E2 on your own. The second one, you had to arrive at the fact that you deprotonated and then you did an SN2. Now, typically, you have to arrive at your own what mechanism you're doing.
You said on the last test that that was the only one where you wouldn't give us, IR.
Spectroscopy.
Okay, so we're not, so we only have to worry about mass spec, it's just not
No,
or?
I didn't say anything like that.
Okay,
I said test 2 is the only one you'll have at me that will not have any spectroscopy.
okay,
And test 2 did not.
okay,
Now, since that's the only one, test 3 will have spectroscopy.
okay.
But mass is not really called spectroscopy. Spectra. Yeah, test 3 will have mass spec. There are combo problems where you could see IR with it, like in the workbook. Say if organic 2, every test in organic 2 will have some type of spec.
Okay.
That's all I was saying there.
Oh,
Test 2 is the only one I give that doesn't have some type of spec. Okay. So everything we've covered will be on the test. I tried to mention the main highlights.
Other questions about the test? Question?
I
Are we gonna get to UV vis or no?
I don't,
Probably not going to do UV Viz today. So UV Viz will not be on the test. We'll cover UV Viz maybe after the test tomorrow or on Thursday. We also have some radical chemistry to cover. Those two topics will be on the exam, but not on test 3. Okay, deuterium isotope effect. A neat way to determine if an elimination reaction is E1 or E2. Look at this reaction. Obviously it's an elimination. We're getting an alkene. E1 or E2?
It says both, but it would be E2.
Is that nitrogen?
What do you need to do in E2?
Strongly.
Strong base. What's the name of that nitrogen compound? Pyridine. Is pyridine a strong base? The lone pairs in what type of orbital? Okay, what did we say were strong bases? I usually said sp3, sp2. Okay, so is it a strong base? Well, here's the take. It's borderline.
You got too many borderline things going on here.
Okay, so is it E1 or E2?
I don't know, both.
Okay, well, here's a neat way to determine it.
Oh.
Okay,
Neither.
it's an elimination is one. Okay, how would you determine it? We asked this question before.
These mechanisms.
No, doing the mechanism is you're proposing theoretical on the board. Then what is actually happening? Okay, there's a difference between theory on the board, and we teach theory, and we're talking theory. But in practice, how do we know? I think Dr. Harger has these BS signs, like you're talking all this theory and someone holds up a BS sign, and this is just a bunch of BS here. How do we know this really works? Okay, well, guess what? All the theory has been put to test, and that's how it became the theory. But still, there's gray areas, yeah? Well, how can you, what experiments do you do to determine gray areas? Well, we can use deuterium here. First off, before we get there, what could we have done? We could have did a rate study, right? Because if it's E2, that means this is involved in the rate determining step, the base. If it's E1, it's not involved in rate determining step. So we could have did it, we do the reaction, determine the rate, then change if we then change the concentration of this and the rate does not change, what does that tell us about the mechanism? It must have been E1. So we could have did rate. We mentioned that before, yeah? Okay. Another way we could do this is deuterium. Replace the beta hydrogen that's being extracted with a deuterium, which is just a fancy hydrogen that has one more neutron. Here's the beta hydrogen that's being extracted. You change that to D. Now, this could take you a lot of time just to get the D there. But let's assume you can do that. Then do the reaction and see if the rate changes. Because let me ask you this. First off, is the carbon, hydrogen, or deuterium bond broken in this reaction? Yes. That's the beta hydrogen has to be removed. But let me ask you this. In which mechanism, E1 or E2, is the CH bond broken in the rate determining step? E1 or E2?
E1 or E2.
Well, what's if this said an E1, what would be the rate determining step?
Just the bromine leaving.
Bromine leaving. Was that bond broken in that?
No.
No. If it was E2, what would be the rate determining step?
The whole thing.
If it was E2, we break the bond, these electrons move in here. Only in E2 is this bond broken in the rate determining step. But you already knew that, right? And if I hadn't asked you today, you would have been able to answer that tomorrow on the test. Because you know the mechanisms of each. Okay, it turns out that a carbon deuterium bond is stronger than a CH bond. You can go back to this mass effect. A heavier atom, typically heavier bond, that's a generic statement, or a stronger bond, but the bond is stronger. Roughly, I think it's about 7 times stronger. So if this is deuterium, the E2 will be more difficult because you got to break a stronger bond here. So what you do is you change this to deuterium and then see if the rate changes. If you change it to deuterium and the rate changes, the mechanism is E2. And if you change it to deuterium and the rate does not change, it must be E1.
So we're not gonna be able to just do it like we do any other reaction. We have to actually do the experiment.
Have to actually do what?
The experiment, right?
What do you mean, the experiment?
Like actually add more concentration. We can't do it like any regular E2, E1 on paper, right?
I'm not quite getting you.
She's saying like, in order to prove this, you'd have to do the experiment versus just drawing the mechanism.
That's the same thing with a rate, though. Number one, you have to do experiments. You would repeat the reaction.
Like for the test, we wouldn't be able to do this to determine if it was E1 or E2.
No, you'd have to be given some experimental results. That
Yeah.
is, when this was done, the rate became much slower. If you know that experimental result, then that tells you that the mechanism must have been which one?
E2.
E2. It's only going to become slower if the stronger bond is broken in the rate determining step. If it's E1, this bond is broken in the fast step. And if you make a fast step more difficult, who cares? Unless you make it so slow that it becomes a rate determining step, but it ain't going to do that here. In general, this is called an isotope effect, because we're changing to an isotope and we're looking for an effect. Isotope studies, isotope effects, a lot of these are done. Deuterium most common. Special topic. More and more recently, drug companies are putting deuterium into drugs instead of hydrogen. And the first drug to contain deuterium is on the cover of your workbook. This is the first drug approved to contain deuterium. First ever to be approved by the FDA. It's actually got 6 deuteriums. The reason that it's there is because if this was just H's, that is the original drug, just H's, non-isotopically labeled drug, this drug is metabolized by cleaving these groups off the oxygen. Hello. And cleaving the groups off the oxygen deactivates the drug. And so the half-life is not as long. And you have to give like dosage 3 times a day or something. Well, that's not good because patients don't want to take drugs 3 times a day. You'd rather give it 1 time. But the drug has to last long if you're only going to give it once. So what the drug company has done is they've slowed down the metabolism by changing these to deuterium. Now they know that when this gets metabolized, the CH bond is broken. And apparently it's broken in the rate determining step. How do they slow it down? They changed it to deuterium, and now it's much more difficult to do this reaction. So it doesn't get metabolized as quickly, and now they can just give 1 pill a day instead of maybe 3 or something like that.
Isotope effect. Okay, product of these reactions here. We can also utilize our information about deuterium when we're considering reaction outcomes. Okay. Anybody have products for the first one? Substitution, what'd you get for substitution?
But there's heat.
No, it's not going to be racemic.
It's inversion.
It's going to be SN2, and it's going to be inversion. Question?
Does the deuterium get to be dashed or wedged? Since it's inversion, are we just worried about the OH?
Why would this carbon undergo inversion?
Because I thought the whole molecule flips.
It's the reaction side.
No, only at the reaction site where the backside attack takes place. Okay, how about the elimination product?
Thank you.
Yeah.
So why do we hold the hop in there, not the
There's no hop on our state so here.
Is there not an H at the, where the deuterium is also, that you could pull?
Yeah, but that H is cis to the bromine.
Oh.
And why do you want to make alkene there? It would be disubstituted just like that one over there. A D is not a substituent. It's just an H with an extra neutron. Not a carbon. Question?
Why would you put the double bond on the LIGO down towards the D?
Here? What do you want to have on this carbon, a D or an H?
You would keep the D in there.
I'm going to put a D here. That means you remove the H, correct? Okay. That H is not anticoplanar or transcoplanar to the bromine. If we drew a chair, shall we do it?
Please.
If you put the bromine axial, why?
Because it has to be.
So it has to be. There's an H and a D here. The D is trans to the bromine. So that means it's down. And the H is like this. There it is. Which one of these is going to be removed? The D or the H? When you do your mechanism.
D.
The D. The one that is trans-coplanar with the leaving group. So if you're going to do chemistry down here, you remove the D. So there'd be an H there. Now if there's an H there, we can just draw it like that. This is where you remove the H down here. This is where you remove one of these H's. No, I'm sorry. This is where you remove the D down here. This is where you remove an H. Which is easier to remove, a D or an H?
H.
An H. Is there anything else going on that dictates one or the other? No. This is just, it's easier to remove the H. Assuming that they both can be removed, they both are anticoplanar. There's two H's here. One is down, and one is like this. Correct?
Yes.
Isn't there one bolded and one dashed? When we put the double bond up here, which H is removed?
The one going down? Right? Or is that?
This one. Which one is this of the two there?
Oh. Yeah, it's gonna be trans, so the dash.
Which one is this?
The dash.
Is this A or B?
A. Wait, now I'm thinking.
Is this A or B? Is this H cis or trans to the bromine?
Trans.
That was quick. How do you know it's trans?
Because it's down compared to the.
This is up compared to the H. This is down compared to the H. This is trans. So which H is it?
A.
A. Yes. That's A. That's B. And this is C. And that's D. We did this 3 weeks ago. These two are trans to each other. HA and BR is trans. Let me ask you over here. Which H is trans to the BR? You would say, duh. It's A. But you got to be able to see it here too. That's why 3 weeks ago we did such. Okay. You're either going to remove this or this. Those are the ones that are anticoplanar to the leaving group. Now, both of them give disubstituted alkenes. So there's nothing that drives it that way. So what can you say what can you say is the difference here? It's easier to break a CH bond than a CD bond. The transition state of breaking this is going to be lower. You're going to get double bond here. And the D will remain. That's what we showed. And there'll be no change in stereochemistry here because we didn't do any chemistry there or here. We did backside attack with inversion there, and we eliminated here. We're bringing it home now, okay? Pulling it all together. Now you see it as blue. Questions? Anything there we have not discussed? Little tiny bit of, well, the only difference here is breaking the CH or the CD.
How about below here? Substitution and elimination. Silver nitrate, I've never seen such. What in the world is that for? Ethanol? What's going on here? Substitution, SN1 or SN2?
SN2?
SN1,
But that AG is gonna pull it off.
to make carbocations,
And make it
SN1.
easier.
SN2 does not
Oh,
involve
yeah.
carbocation. SN2 requires a strong nucleophile. Where's the strong nucleophile? You might say nitrate. No, well, it's not. Nitrate is like sulfate. It ain't gonna never attack anything. At least not in this class. Ethanol, weak. SN1. Somebody got product. Now be very careful here. When I show you the product, you're going to say why. And then I'll explain and you'll know why. Product is going to be
Shift it.
will be then racemic, right? Yeah?
Yes. I understand.
How do we get that? How do we get the nucleophile bonded here?
As you shift it, hydride.
I did a hydride shift. Right? What's the first step of the mechanism?
The chlorine leaves.
Okay, does anything help it leave?
Yes.
Coordination to the silver, or there's some type of something going on there, but, okay. Let's just do it. Cation, ethanol could attack here, or what else could happen?
Hydride too.
Hydride shift. We said a couple of weeks ago, anytime you do a rearrangement, do that. Rearrange to what? I'll draw the ring out here.
Resonance stabilized cation.
Yes. Still secondary, but resonance stabilized. Much better cation. Then what? Ethanol attacks. Which side? Front or back?
Either.
Either side, correct? I'll let you finish it up. You got to remove the proton. It doesn't just magically disappear. It's not. Oh, I think it was magically delicious. It ain't magically something. Both sides. Carbocation chemistry, rearrangement, yeah? Okay, what about elimination product? It'd come from the same thing. It would just eliminate from here. Something would take the H. I mean, you could use ethanol to take it. You could even use Cl minus to take it. Your choice. It's just about anything to take it. Take an H. These electrons move in. And you're going to get boom, 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 boom. Here. This thing can rotate. Or even get cis or trans over there. Trans, because trans is better. Whenever you do an E1, which alkene do you get?
The most stable.
The most stable, yes.
The
Most stable. This last step is actually in equilibrium. A lot of this is in equilibrium because, look, we produce this plus HCl. Well, 2 weeks ago we were reacting alkenes with HCl, right? This attacks and we get carbocation. We were going this way 2 weeks ago. Okay, here we go. Double E2 elimination. That's the lab tomorrow and Thursday. It's not a new James Bond movie. It's a way to make alkynes. Just do
2 E2 eliminations. But we're going to have to sort of show an exception, something that says, well, hold on, I didn't think we could do that. Decimal dihalide. They're not twins, but they're in the same vicinity. 2 equivalents of a strong base. The oxygen anion can take the H. These electrons move in here, kick that off. Now, see, you could do either. I could have eliminated this H and that Cl. You could do either. We're not going to. This will give. That alkene, if we were to eliminate HCl. Can we eliminate again? Can we eliminate another HCl to put in another pi bond here, make an alkyne? If we were to show that intermediate, can we eliminate again? Well, according to the directions, we can. Okay? Which H are we going to take, top or bottom?
The one
The one that is transcoplanar to the chlorine. Which one is transcoplanar? They're all planar. They're all in the board. Which one is transcoplanar? This is trans to the chlorine. You can't rotate here. And the base takes it again. Boom, boom, boom. What does that give? Triple bond. But you say, what's the problem with this? What's the problem with this? This chlorine is not on a tetrahedral carbon. How's it leaving? Well, that's why I'm doing it at the very end, so I can say it and then run out.
What?
It can happen. This requires a lot of heat. If I'm telling you it can happen, how else are you going to show it, the second elimination? Because once you put one pi bond in, now it's there. This is the only place it should ever happen. Can it happen? Well, let's go to lab tomorrow and Thursday and take your dibromide and let's reactive it to equivalents of base. Let's see if we can get an alkyne. Okay, here we go. I know we only got 30 seconds left, but let's summarize it here. Here's a flow chart for predicting your reactions. Okay, if you give me a minute, I'll look at this real quick with you. Flow chart. Is there an sp3 carbon with a leaving group? If there ain't, no matter just what we just said, you ain't doing none of these reactions. Should we go over this or no?
Yes.
Yes. Okay, if there is, then you can do any of them. That is, if you have a leaving group on a tetrahedral carbon, you can do any of these reactions. Okay? Is there a beta hydrogen? Because if there's no beta hydrogen, guess what? You ain't doing an elimination. You already know all this. You already know all this. If there is a beta hydrogen, then you can do. Okay, I'll send it to you.
Okay.
Now, I could have started with this, and you all would have gotten all like, you already know all this. Okay? So, is the beta hydrogen coplanar with the leaving group? Because if it ain't, you ain't doing E2. Let's get on down. I'll send you this by email. Let me see what they say down here. Is a leaving group on a primary carbon or tertiary? Because it's on primary, guess what? You're only doing SN2. We're under substitution over here. If it's on tertiary carbon, you're only doing SN1. You already know that.
What if it's on secondary carbon? Both are possible. Well, what about solvent? I wish they call it protic product. What if we say polar solvent? Polar solvent is going to facilitate which one more? Ions. Polar. So which one is ions?
SN2.
SN1. So I wish they had a little bit different here. Heat. Are you heating? Which one does that favor? Elimination. Okay, you know all this. There'll be one or two new things on here. Please don't freak out about this. Okay? That's why I give it to you at the very end. Okay? This is somewhere out there. I'll send it to you. You can look at it. Use it to confirm what you know. If there's any questions you can ask, but probably it's not going to be totally relevant if we just never covered it, because I just chose not to. There'll be one or two things here that we just really never even looked at. Looks like a lot, doesn't it? But if you know what we're doing, you know all this stuff. I'll send it to you so you can just confirm. Don't freak out. Oh. See some of you in lab this